Thanks for having me. My name is Lynn. I'm from Bureau last year in August. So previously, I was doing my PhD, which is focusing on the computational fluid dynamics, solving the Navier-Stokes equation, new numerical schemes, and thermal fluids like buoyancy-driven flow. So that's my background. So today I'm going to talk about the ACCESS-MICAS, which is a forecast-based tool for event attribution. So this is an example that we use a coupled model for event attribution. So I'm now going to my next slide, so if you can see it. So what is event attribution? So the research question that we always have is, when an extreme event occurred, people are wondering, does climate change makes it more extreme? So is there any climate change component in an extreme event? So to solve that question, there's a lot of existing method. Most of it is statistical. So one of it is just comparing the HISNet CMIP data, which is with only natural forcing compared with historical plus scenario, and then see the chance of such an event. And also, one can explore the variability, the climate variability in the PI control, and also come to his scenario MIP to compare the chance for such an event or shift of PDF for such an event. Or one can look into the detection and attribution MIP, DAR MIP, or any single forcing MIP force to look at and contribution for any contributor. So the problem for using this kind of method is that it's never the event. So no extreme events are the same. So every extreme event is different. So you will never ever capture the event. And also we have huge model uncertainty in the CMIP. So a different model will give very different answers. And also if we only look at a statistical process, then that means you don't have any information in the processes. So that's the motivation why we propose this forecast-based attribution system, because we can always capture the event in a forecast model, and the model only run a snippet of time. So that means we suffered from less model biases using that method. And also it's very easy to look at changing process because you have that cutoff time. So the forecast model we are using is ACCESS-S2, which is a global coupled dynamic model. It's from a GC2 family. Glossy 5, which is global seasonal forecast version 5. So the UN version it used is 8.6 with jewels, Nemo Ocean, the sea ice, and also straight coupler. So the resolution we have is N216. The horizontal have the horizontal, and vertically we have 85 levels, and the ocean is a quarter degree with 75 levels. It's run by a road silk configuration. So usually the model runs through subseasonal to seasonal scale, which is around 6 weeks up to 7 months. And we do an ensemble forecasting, where the ensemble members are generated by perturbing atmosphere only. And we have the capability of generating 33 members per forecast start date, and which requires perturbation files. And also we have the atmosphere, land initial condition, the ocean initial condition, the sea ice for any start date from 1981. Because the model is operational, so we have it for every single day, start date. Regarding the cost, one model step is around 7 days. It's set up in the model, and it costs around 300 service units per member, which makes it, if you want to run a 9-member ensemble for around 4 months, that will sum up to around 50K SU. And to run in ACCESS-S2, you need to require access to the X2 project, which is a bureau project. So how we use this forecast model to attribute an event to climate change. So in a forecast, we look at the event in the forecast, which means that a forecast have a start date with some realistic initial condition. And then the dynamics in the model can forecast this event in a present climate. So what all required is just the initial conditions and the models. So if we want to reforecast the same event, but in a past climate, we just need to modify our initial conditions. And then we just run the model, free run, and then we can forecast such an event in the past climate. By comparing the event in the past to the event in the present, we can attribute the differences to the climate change. So the problem is what modification we need at initialization to make all these conditions in past climate. So definitely we need to change the greenhouse gases or CO2 levels and all the greenhouse gas concentrations. But the problem is there any other things that we need to change? So we start with changing the greenhouse gas concentrations. So this is a list of table of the greenhouse gases that we consider and their value in the past and present and future climate. So if we only change the greenhouse gases like CO2 or the greenhouse gases, we just pick one event, which is the Black Summer in 2019 to 20. And then we initialized on the 1st of December, and we look at the summer DJF following. And we do 3 test cases: the control run, which is a rerun of the operational forecast. We did 9 members. And also we did a low CO2 run, which is only changing the CO2 concentration to past climate with no any other modification to the initial conditions. And also the low greenhouse gases run, which changes all the greenhouse gases, but still no modification to the initial conditions. So here on this figure, I shows the time series of the global mean surface temperature and Australian mean on the right, and also the time series for the outgoing long wave radiation. So in this case, we can see that the response there's a response in the surface temperature globally and also in the OLR. Generally, the control has the higher surface temperature and then the low CO2, and the low greenhouse gases gives the lowest surface temperature. But their differences is very small. They are growing with time, but the response is reasonably slow. So although we can similarly we can see the response in the OLR, the response in the OLR is instant, but generally it's still very slow. And also we can see that the trend in the global mean is very clear, the differences, but in the Australian mean it's not that obvious. So that gives a hint that only changing the greenhouse gases is not enough to speed up the system. So we don't want the system still be in a transient state while we just lose the scale to forecast this event. So what we do is we consider to include also main state changes in the initial conditions. So how to derive the main state changes for a past climate and present climate? We use a single GCM's historical plus scenario run. So here we find UK Madoff GC2 historical plus scenario runs using a CMIP 5 forcing. There's 5 ensemble members that we have, and this one is using RCP 4.5 since 2005. So what we do is we pick the 1861 to 1950 as our pre-industrial period. Based on the temperature, we can see it's reasonably leveled in that period. That's how we pick it. And then we choose 2001 to 2020 to represent the present climate or post-industrial climate. And then we derive a monthly differences between these two climates and to represent our mean state changes. And we look at mean state changes in only the several variables. For example, the air temperature, the specific humidity, where the differences show the top is the air temperature at the surface and the top and air temperature zonal main. And similarly, the bottom row is for the specific humidity. This is how this looks like in a single month. Like for this case, it's September. And then ocean temperature and ocean salinity. This is the ST patterns and slides at the tropics. And similarly, at the bottom, there's the salinity and the slides at the tropics of the salinity as well. We also take out the soil temperature and the moisture from the model to accelerate spin up. And on the left panel here is the soil temperature in all 4 layers. And on the right is soil moisture differences in all 4 layers. So this is how they look like. So the reason we choose that data set to generate the mean state changes is because it has the same horizontal resolution as ACCESS-S2. They have very well resolved stratosphere, 85 levels, and it's the same land model. And we can know that the mean state changes, especially the soil moisture, is very model dependent. So using the same land model can ensure us that we get a consistent results. So the drawbacks for using that model is that from the time series, you probably can already see that they have very strong response to the aerosol, that model. And also, if we look at the differences of temperature near the surface, it's around 0.6. So the response so generally, the differences due to climate change is reasonably small. So we did 3 other experiments testing the effects of the mean state changes. So the blue one here is with the past climate greenhouse gases, but also the mean state changes in the atmosphere and ocean, but nothing in the land. The orange here is where we include the soil temperature differences in the initialization as well. And the green one is including everything. So here, similarly, I still shows a time series of a global mean surface temperature, OLR, and also their Australian mean. So now you can see the differences. The response due to all these changes is reasonably fast and is very well maintained. So it gives a hint that we do need to include the mean state changes. And here we tested different soil moisture cases. So here, similarly, still a time series, the global mean and Australian mean, and it's first layer, second layer, third layer, and the bottom layer in the vertical axis. And then the left panel shows the soil temperature time series, and right shows the soil moisture. So basically, it's a little bit messy. I apologize for that. But basically, what we can see is in deeper soil, the blue curve tends towards the orange and the green. So blue is without any modification to the soil temperature, and the green and the orange is with the modification to the soil temperature. And you can see that the blue goes to the green and orange, which indicates that we should include the soil temperature, because if you don't modify it, it will still go into the same direction, but at a very slow rate. So similarly, in the soil moisture, we can see that those without modifying the soil moisture, the blue and orange goes towards the green, which with modification of the soil moisture, especially in the deeper layer, and the rest is very slow. So that gives a hint that we should include the soil moisture in this case as well. So a key variable for that event is the T max. So here we demonstrate the T max in the southern hemisphere in a large scale and also in Australia itself. So the top row shows the control anomaly forecast, and the second row shows the difference between the control and the low greenhouse gases with also modification. So basically in the direction of warming, so basically indicates an effect of increasing greenhouse gases. And also for this case, we conducted high greenhouse gases scenarios as well. But to do that, we simply just flip around our main state changes. So we just, rather than remove the main state changes, we add on the main state changes and use the future climate greenhouse gas scenarios. And we put it in a direction of warming, which indicates like an increase in greenhouse gases. So from these results, we can see from the middle plot, the difference between the control and low greenhouses, we can see that almost the whole Australia was hotter than it would have been in the past climate. And if we look at the numbers, during this event, 1.3 degree night, which was the first plot in Australia, 0.8, which is this, the area integration of that is attributable to climate change. So this is a statement that we can say about that. If we look at the future scenario cases, we can see that if this similar condition occurs in 2050s, which is the baseline we choose for the future climate, this event would be another 0.9 degrees hotter than it was in 2019 to 20. So we have done a lot of experiments already for different events. The black summer is one of it. We also tried to do some rainfall events for the wet October in 2020, the wet spring, the warmest July for Tasmania in 2023, and also warmest winter in 2023. So if you have any interest in exploring all these experimental data, please let me know. These are already available. So some future works that we plan for this. The first one, we plan to change the dataset that we use to become CMIP6 model, the HETGEM3 GC31MM. The reason why we change this is because previously I mentioned that GC2 has a very a small delta that we have, which is around 0.6 degree at the surface, which is not much smaller than what we observed. So we hope that using a better model and a better forcing, that can give us a better representation of our delta. Also consider using a multimodal deltas, but the problem is different model has different resolutions, and it could be very different soil moisture differences if we use that. Also, we plan to use a better baseline to represent past and present climate using 1850 to 1900, which is aligned with the IPCC report, and 20 years centered at an event year, which probably makes more sense in this case. And the problem that we would like to look into is the delta in the ocean. So as we know, the CMIP6 models generally have an El Nino-like pattern, which is more warming in the Eastern Pacific and less warming in the Western Pacific, but this is not as observed. So the observed trend is more like a La Nina-like shape. There's been a lot of discussion around that. So currently we're using a model SST difference, but if we can apply observed trend into the model, it probably can give us better representation of this event. So two questions get asked a lot. The first one, does the model, this modification at the initial condition just perturb the event away from the extremity? So to address that question, we do is that we run a high greenhouse gas experiment. So generally we expect the response to the greenhouse gases will be consistent. So if running the high greenhouse gas experiments gives you a similar result, similar response to the increasing greenhouse gases, then we are more confident to address that question, says we do not perturb this event away. And also in this case, our delta we applied at the initial condition is generally smaller than the initial conditions anomalies. So that's another way we say why we are not, we are confident that we still get event in this low greenhouse gas experiment. And definitely an easier way to do it is generate a low greenhouse gas hindcast by looking at the event in the low greenhouse gas hindcast, and then we can capture this event to say it's still extreme. So another question we get asked a lot is the counterfactual initial condition realistic in the past climate? To address that, we plan to create a weather analog using our CMIP PI control to explore all the natural variability that is possible to get in the past climate. So what else this system can do? So this system is capable of doing a lot of other experiments besides analyzing the effects on the climate change. So here I will provide 3 snapshots of what other experiments we have done using the same system. So this one is very similar to what UPA previously proposed in the ACCESS Hive. So we analyzed the role of tropical ocean conditions in the wettest Australian spring in 2020. And then we look at the effects from the ocean and also the effects from the atmosphere initial condition. Here we done climatological ocean initial conditions, which we replace the ocean temperature, salinity, and currents to their climatological conditions, and do another set of experiments, which is randomized atmosphere, which is what I guess proposed for the triple La Nina. So randomized atmosphere and land initial conditions by randomly selected between this baseline. So we can see this event is very well cast in ACCESS-S2. And if we look at the experiment that we done initialized on the 1st of September and look at the rainfall, which is the last series of bars, we can see that the differences between the orange and green is attributable to the ocean conditions, while the differences between the orange and red is attributable to the atmosphere initial conditions. So the atmosphere, for this start date, the atmosphere plays a more important role than the ocean in terms of the rainfall. Another experiment that we have done using the same system is trying to understand the polar vortex strengthening event in 2020. So during that time, there's an unusual strengthening. There's no dynamic processes, and it's very poorly forecast in ACCESS-S1 at a time. So we're trying to understand, is there anything missing in the model, and if we add on it, would it improve the forecast? So one thing we found missing in the model is a realistic ozone concentration. In the model, it used a climatological monthly ozone. So at that time, it was a large ozone anomalies, and it's not actually in the model. So what we do is we run real ozone experiments by replacing the climatological ocean concentration in the ancillary file to a realistic ozone concentration. And then we just run these experiments from a certain start date. Then we also look at the realistic ozone, but with climatological ocean to look at the effects from the ocean as well. So here on the right, I plotted the temperature over the polar cap. The x-axis is the time, calendar months, and the y-axis is height, where this blue hot spot is the cooling, which is the strengthening of the polar vortex. And you can see it moving down to the surface with time. So we can see that compared with the control norm is not capturing it very well. The real ozone has forced strengthening of the cooling and the strengthening of this event. So with the real, that means the ozone plays an important role in this event. So this row shows the realistic ozone, but climatological ocean. And you can see this the blue region just get less. So which means that ocean also plays a little bit roles in this event. So the last snapshot that we have done is for the Tonga volcano eruption on the 15th of January in 2022. So at a time, due to the eruption of the Tonga volcano, it has 100 teragrams of water vapor anomaly in the stratosphere. And we know that water vapor will stay very long in the stratosphere. So we're trying to look at its short-term and slightly long-term effects on the climate. So what we do is we grab the observation from the satellite, vertical distribution of all these water vapors, and then we just add it on in the ACCESS-S2 system, and then do a forecast. So here it shows like an illusion of where this extra water vapor goes with time. So you can see it's generally capturing a very good travel over this kind of water vapor, and we will look further into its effect on the ocean and atmosphere and other events. So a quick summary. So the event attribution, we majorly look at the role of climate change in extreme event. The forecast model that we are using is ACCESS-S2, and it has its strengths because it's an operational system. We have a lot of resources available. So the ACCESS-MICAS that we reforecast a certain event and then compare it to its control to tell the contribution for the climate change. So it shows how we apply a forecast model in an event attribution study. So when we do attribution to climate change, we modify the greenhouse gases and also include the main state changes in atmosphere, ocean, and land. And we look at how it looked like in a Black Summer event as a case study. So what else this system can do? Well, we can explore the role of different components of the model, ocean atmosphere. Also, we can look at different ancillary files and their effects. Also, effects. So to understand extreme better, it gives us to forecast skills and address some research questions. We have a triple line here. So each time we have a
thank you so much.
And then we have
Sorry, Lynn, I get confused if you were finished or not. You were cutting a lot. So if you do want to say something on that slide, please go ahead. You've been cutting a lot for the last few minutes.
sorry. We have all.
It was great until the last slide. Now we just lost you again. Okay, yeah, we can see your slides. Okay. Okay, so I guess you're done now.
Any other?
Yeah, we can't hear you anymore, Lynn.
I would suggest stop sharing and then maybe we can hear your audio.
Yeah. Okay. Well, it was very good talk. Thank you. You did a lot of work. We could hear most of it.
Sorry about that. Sorry that the connection is not very good.
It was just the last two slides, I guess, where we lost.
Oh, okay.
Yeah, no, the rest was very clear.
Thanks.
And you also answered a lot of the questions, so I don't know if you'll have many because in one of them you just started to answer all of them. But anyway, does anybody have a question for Lynn?
Yeah, I just had a question about the time step. Well, you mentioned the model step was 7 days. I was a bit confused because you know, one of these models would have.
Yes.
What do you mean by step?
Like,
and yeah.
yes, so it's more like artificial thing. So we just model step, and every time submit the size of the job into the guide. So it's nothing to do with the time step inside the model. So inside the model is still like an whatever 100 days or 6 like steps for or something. Usually just 7 and it's a job, and then to the next time you submit another 7 guide. So like this is the big kind of cycle with how you run the model.
Look, I'm really sorry. That audio is starting to really cut out a lot. So,
do you want to cut off your video, maybe, please?
Yeah.
Oh, I probably will stop my video. Is that better? Sorry about this. I don't expect it to have so poor connection here. Sorry. So
your audio is flawless when you have the video off, so you don't have to worry about it.
The 7 days is. So the 7 days is what you submitted to the Guardi. So inside the model, inside the 7 days, it's still like 107 steps or 96 steps for UM or something like this. But 7 days is a kind of a chunk of jobs you submit to Guardi, and then you just run it 7 days, and then you get off, and then submit another 7 days. So this is kind of a larger model step for what is run on Guardi. So it's kind of we manually cut it to become 7 days, like a weeks, which is easier for us to process, and then 7 days costs around 300 KSUs. 300 SUs.
Thank you. Shoban?
Hi, Lynn. I raised this question before when I saw you give this talk. I think it was at the BOM meeting. And I definitely think there's an extreme sensitivity, obviously, what's going on with the soil moisture. But you were talking about moving from the GC2 run, which I think is obviously that's an older one because it matched with the ACCESS-2 to the now the adjunct-free GC-free CMIP6 runs. But I'm wondering whether the soil moisture setup will be as similar. Obviously, it will still be joules based, and obviously, I think I may have started talking to Rachel about possibly whether the cable setup will be also of interest to you. So I gather you're going to visit us next week, so that will be interesting. And to look at some of our data as well, because that will be interesting to see what's happening with those ones. Because I think this delta is quite introducing quite a lot of sensitivity into the runs. But I'm also interested to know how much sensitivity there is to the ocean, this ocean delta in the system, and I think that's probably something that could be quite important, because it's also a case of how big this CO2, these CO2 and greenhouse changes are causing this response and all these greenhouse gases. Because it could be because, as you say, you might want to look at a multi-model response and how much that is causing the response as well on these extremes as well as the individual models. Because I know Pandora initially started these extremes testing in Pawama and trying out this approach, and obviously now you're developing it with ACCESS-2, which is good using the most recent model approach. But yeah, I think it's quite interesting to see how sensitive it is to the methodology. But hopefully we'll chat more next week.
Yeah, we are currently testing. Cool. We are currently testing the GC22 and GC3 delta. So in terms of ocean pattern, they're still more like El Nino-like. So it will be different from the observed. I think Umi insisted that we should use the observed ocean as it has huge effects on Australia. In terms of soil moisture, we are using similar technique, but the GC2, we use a ratio, like percentage. But it will have some problem in the GC3 for some months. So we are currently using differences, but still like the same. Cut at like climatology, 2 baselines, and then say the differences or something like this. In terms of structure, they are similar in GC3 and GC2. And yeah, they're very similar, but magnitude is different. GC3 has a much stronger response, like due to the increase in greenhouse gases. It's around 1.3 degrees from now in terms of relative to the past climate.
Okay, so that will be interesting to discuss more. Okay.
Yeah, nice to Talk to
Thank
you
you,
next
Lynn.
week.
Are there any other questions? No? Okay, well, thank you so much, Lynn, for your presentation, which was very interesting. And sorry we had those connection issues.
Thank you for having me.
Yeah,
Sorry, it's probably on my side that has the problem.
yeah, no worries. Okay, are there any other topic of discussion that people would like to raise? Have a few minutes if you want to. Nothing? Okay, well,
Sorry, I mean, I could just mention that in following up on this myosine stuff, like we've got a myosine test case running on ACCESS-ESM, so it's a bit of a step forward compared to what I presented in the past. So I just thought I'd mention that as an update.
congratulations, David. That's great to hear. Yeah, so David's done a lot of work and progress on modifying the land sea mask and adding land to where there was no land, therefore vegetation and others. So please do read this post if you're interested. But I think if I understood correctly, you'll give a talk in November?
Yeah.
Okay. Okay, well, I guess we can stop here for today. Thank you, everybody, for joining, and we'll see you in 2 weeks. Bye.
Bye.
Thanks, Laurie. Thanks, Lynn.